Okay.
Okay, good. So, thank you for not inviting, thank you for giving me opportunity of this talk at Will's MPPM seminars. As David told it, this is the first time since I gave it 20 years ago. And it's pity that it's over Zoom and this time and I cannot visit Wales. But anyway, today this is somehow. Today I talk about the new proof of this Lubetzky and Peres theorem that it's about cutoff phenomena in probability theory. Although the theorem is only 5 years old, there are already 3 different proofs. So mine is the 4th proof. In that sense, it's not that significant, important, but I'm very happy about this new proof because the previous proofs are all by hard analysis, and my proof is mine is very soft without any actual analysis. Soft analysis or functional analysis, they are the same to me. And I'm a big fan of the functional analysis in the rivalship or rivalry between hard analysis and soft analysis. Yes. So today the talk is about random walk. Random walk on a deregular finite and connected graph, which is non-bipartite. So the random walk is it's a person, guy walks completely randomly without any memory where he is or where he walked. He sometimes backtracks, etc. And then so the simple random walk is in time t is in integer, is written by xt. And the transition probability is that the transition probability is just given by the adjacency matrix, which is normalized, the self-adjoint matrix pxy. I don't know, how do you see it? And the distribution of mu, do you see the red button, red circle?
Yes, yes, we can see it.
Good. Then this mu t denotes the distribution of xt at the time t. So in fact, I take not this random walk view. I take a statistics view that actually random walk starts at the x0 origin, like 1 million people starts a random walk, and so at the time t, this point populates some certain amounts of people. This point populates certain amounts of people like that. Not the single person are walking. Millions of people are doing the random walk at the same time. And then the mu t distribution eventually converges to the stationary distribution. And the stationary distribution is nothing but uniform distribution because the graph is connected, so that there's only one connected component. And the graph is not bipartite, so in the end, the stationary distribution is uniform. This is easy to show. If the graph is bipartite, then at the time odd and the time even, there are the parts you cannot visit in the time odd time and in even time, etc. But graphs are always connected and non-bipartite. Occasionally, or often, I compare this random walk with the random walk on infinite deregular tree. Infinite deregular tree is bipartite, but let's not care about that. example of this graph I'm interested in. So the random walks model of many things like diffusion process, card shuffling, etc., etc. But in mathematics, I'm particularly interested in the finite groups coming from residually finite groups. So the residually finite groups like gamma is SL3Z. As a matter of fact, 2Z is enough, okay, too. But SL3Z and fix a finite generating set. It's elementary matrix, 1, 1, 1 on the diagonal and only one on the off diagonal some pair. Then this is a generating set. So there are 12 generating sets including the negative one. Then the gamma has a finite quotient SL3Z over NZ, and the adjacency is defined by X is adjacent to XS for any generating set S and any X in the point. So I view graph as just a set of vertices. Yeah. And the random walk in this case is just putting generator elements in the generator from right to the right every time. SIs are independent and uniformly distributed over this generating set S. So the distribution mu t at the time t is t's convolution, t-fold convolution of the uniform measure on this finite set S. Then these graphs are called so-called expander family. It's a sequence, expander sequence, and I will tell you what are expanders in the next slide. And this is S regular transitive graphs. Cardinality of S is 12, so the D is always fixed in my talk today. But the size of graph tends to infinity. The important point of this graph is that the projection from this infinite group, the parent group, onto the finite quotient is injective on a ball of radius something size proportional to log n, because until matrix multiplication, the entries of matrix multiplication grows at most exponentially. So the until t is something proportional to log n, you do not feel the effect of n at all. They look all the same to the unit, to the ball of the gamma. So this is called the injectivity radius. So the random walkers do not notice where they live. They live in gamma or they live in the finite quotients until some time like log n. Typical theme of random walk on finite graphs is that when do the random walkers, when they notice that they actually live in a finite world, when they feel this n, this is something happens around some constant times log n. I explain what the expanders. This is a beautiful picture of expanders I borrowed from the paper by Lubetzky and Peres. Actually, Ramanujan graph. So G is a finite irregular non-bipartite graph. D is fixed always. Then the P transition matrix, it's a normalized adjacency matrix. It's a self-adjoint matrix, and it has eigenvalues. The top eigenvalue is 1, and its eigenvector is a constant function. And this is simple eigenvalue because the graph is connected. The smallest, negative eigenvalue is not -1. If its eigenvalue, it has eigenvalue -1, -1, then the graph is bipartite. So the reduced spectral radius, meaning that the maximum of the modulus of eigenvalues, save for this one, is strictly less than 1, and this is called the reduced spectral radius. And we say a graph is expander sequence, or actually always my graphs can be considered as sequences, but I hate subscript, so it's family of graphs. Expander family. If this spectral gap 1 minus rho g is uniform, that's the supremum of rho g is less than 1. So why it's called expander is that it has expanding property. Expanding property is that given any subset A in G, the neighborhood boundary of A, this is a vertex boundary. Vertex boundary is at least has a size proportional to A. That's this is 1 minus rho g spectral gap, which is uniform, and the size of A, and it's proportional to 1 minus proportional to size of A. But this cannot. But of course, if it cannot be proportional to size of A, if A is G itself, there's no boundary at all. So you need a correction term. Correction term is 1 minus this one. So if it's size of A is at the most 1/2 of the size of G, it's always grows like exponentially. And after a half, the complement reduces by exponentially first. So colloquially, this means that if 1% of populations are infected by this strange disease, you know what, and they spread this disease to their friends, then the 99% will be infected soon. Soon means that it's independent of the size of G. It's exponential. That's why there are lockdowns sometimes. So this is the expander property. Size of G is unbounded, but D is bounded. D is fixed, and still you have this very good connectivity. Examples of expanders are found that the random irregular graphs are expanders. This is used attributed by Pinsker, but nowadays people detected that Kolmogorov did it in '67, but paper in Russian. And the finite quotient of property T groups are expanders, like quotient of SL3Z. Even SL2Z, they have the property tau with respect to this SL2Z over NZ. And the finite quotients of amenable groups are never expanders. This expanding property is already surprising, but if it does not impress you, there's another surprising result about expanders. There are tons of results about expanders, but this one is not. This one is cute. This is an expander sampling theorem. One considers the expander graph G and the random walk, simple random walk xt on G. But this time, the initial distribution is uniform, so it does not start from some fixed point. It starts a random point in G. And you are given a bounded function f with supernorm is normalized, and you want to estimate m mean of it. You want to estimate. You want to know the mean of it from by the statistics viewpoint. Then you can do it in the following simple way. That's just you average this random walk xt, value of random walk up to time t. Then this already actually a good guess for this mean value. That's difference is up at this difference larger than epsilon with very small probability. This is quite surprising. If you can sample arbitrary points every time, so that you need for this you need log G size random bits and T many. Then you of course by law of large number you can estimate the this M. But actually, to estimate M, you don't need that many random bits. You need only first one has to be big log G, but the others are just simple random walk. Colloquially, that if you are given a huge cake and you want to taste what you want to know how cake tastes, and then you just poke your finger to random points and scoop a little bit and taste it, and then you know all whole cake how it tastes. So this is quite surprising, but unfortunately, oh, by the way, this is logically not related to today's talk. If I find the connection, I would solve some nice problem, but I couldn't find the connection to today's talk because the initial distribution is uniform. So the typical theme is that the when random walkers notice that they live in a finite world and how the world is large, how large the world is. So today's measure is that we measure it by total variation distance. Total variation distance is that for given two measures, the total variation is just total variation. It's a 1/2 of the L1 norm. By the way, some time ago, I can't remember who it was. Some famous analyst gave a talk, colloquium talk, and he told us functional analyst that the real strong mathematician, real strong analyst works on L1, this L1 estimate, and not on L2 estimate, etc. So this is about L1 estimate. And the total variation, the mixing time is that given alpha between 0 and 1, at the time that the mu t is close to pi to alpha, within alpha. And so the theme when the random walkers notice that they live in a finite world, and the next thing is that when somebody, 1% of the population noticed that they live in certain size of the world, do 99% notice it soon, simultaneously? And this is called cutoff. Cutoff phenomena is that the distance between mu t distribution at the time t and uniform distribution, of course, drops from 1 to 0. But sometimes it drops gradually like this. Certain parts, it's always exponential. But anyway, in middle, you don't know. Sometimes it's gradually. But sometimes it drops abruptly. That it's 1, and then it drops abruptly to 0, near 0. And this is called cutoff. This is popularized by Ardos and Diaconis, who studies the cutoff phenomena for random shuffling, card shuffling. Card shuffling, so that they asked that how many card shuffling you need to really shuffle the card. And they discovered that there's a cutoff phenomena that I can't remember exact. I should have checked the paper. They proved like that if you shuffle card less than 6 times, it's not mixed at all. But if you shuffle the card 7 times, it's already good, and after 7 times, there's no point of shuffling anymore because it's already after cutoff. Something like that. And because we are not talking about single card, we have a family of graphs, and we say it exhibits cutoff if this cutoff time at alpha cutoff time is independent of alpha between 0 and 1. If G is large enough. Yeah, is this clear? And by the way, this card shuffling is that if card is larger and larger, card shuffling is not the D-regular bounded D. That's a cutoff phenomena is studied in many settings, and today we are studying this cutoff for fixed D-regular graphs. And the conjecture by Peres is that the transitive expander graphs should exhibit cutoff. Or I should have explained what transitive graphs means. That the transitive graphs are graphs that the graph automorphism acts transitively. So the finite groups are transitive graphs. Finite groups group acts from the left, and it's graph isomorphism, so that its graphs are transitive. If graphs are not transitive, it can be quite arbitrary that you cannot expect cutoff. And indeed, there are counterexamples that there's no cutoff for non-transitive expander graphs. But transitive graphs are nice, and Peres conjectured that the transitive expander graphs should exhibit cutoff. There are tons of results of cutoff phenomena, but most of the results are about specific models of like random graphs or etc., or some random model or certain specific groups, etc. And there's no result like this general abstract result. The rare case is that the Lubetzky-Peres theorem appeared in GAFA in 2016, is that any family of asymptotically Ramanujan graphs exhibits cutoff. I'll explain what Ramanujan means. Anyway, as I told you, that there are already two more different proofs by Harmon and Bordunov-Lacroix. Ramanujan graphs are the, so to speak, the best expanders. So how good can expanders be? The expanders are graphs with a uniform spectral gap, and it's better if the spectral gap is larger. So if the reduced spectral radius is smaller. But reduced spectral radius, rho g, cannot be small more than this 2 square root d minus 1 over d if g is large. This value is actually the spectral radius of the simple random walk on the D regular tree. And this is Aron-Popan bound is a general fact that if a random walk is covered, that if a family of random walks, a sequence of random walks are covered by some infinite random walk, then there's like this spectral bound. Spectrum is bounded by the spectral radius, bounded below by the spectral radius of the covering random walk. And the families are called asymptotically Ramanujan if it marks this lower bound. It's called Ramanujan if it's really you get the other inequality. It's allowed in the finite case. Yeah. First examples of the Ramanujan graphs were discovered by Lubetzky, not Lubetzky. Lubetzky and Lubetzky are different persons. Lubetzky, Phillips, and Sarnak. They used the solution to Ramanujan conjecture by doing in the construction, so they named it Ramanujan graph. And later, Friedman confirmed Aron's conjecture that random irregular graphs are asymptotically Ramanujan. Now we have a far-reaching result by Bordunov and Bruno Collins that random D permutations are asymptotically norm-free. That's if you if you cut the trivial part, then it simulates a free group in norm. Now this cutoff, about cutoff, how fast can random walks mix, how small the total variation mixing time is. The total variation mixing time is at least the 1 over HD times log G, when G is large. And the HD is this value. This value, if you know a little bit about random walk, this is the entropy of the simple random walk on the D-regular tree. So and there's always TG mix is bounded below by this, and TG mix alpha is also bounded above by some constant times log G if the group is expander if the graph is expander graph. In fact, it's always bounded by constant times 1 minus log log G over 1 minus rho G. So the proof of this entropic bound, I give you because it's simple, I give you the proof of this entropic bound. Mu t is a distribution of xt at time t, but the xt backtracks at the probability 1 over d. So probability 1 over d, it backtracks, and 1 minus 1 over d, it goes forward. So it's concentrated on the ball or sphere, around sphere of radius at the d minus 2 over d times t by the law of large number, with error term something like square root t, size of square root t. And so this has cardinality at the most if there's no overlap at all. If it's a tree, it's a cardinality of this. If mu t is close to pi at the t with at least epsilon close to pi, then this cardinality has to be proportional to the size of G, which means which results that the TG mix alpha is like 1 over HD. This HD is the exponential growth rate of this size. Yeah. So actually what Lubetzky and Peres proved is that it's not about cutoff. It's about it's a theorem that the Ramanujan graphs marks this entropic bound. So the Ramanujan graphs by definition is graphs marks this Aron-Poppan bound, and then it attains this entropic bound. Now the proof is my proof uses it's already clear that somehow entropy has something to do with this phenomenon, but and there are several results which uses entropy in the cutoff context, but they are not that explicitly using entropy. I use entropy very explicitly. So what is entropy? Entropy or Shannon entropy of the measure nu is given by this formula. It's difficult to tell why this is a right formula, but it's if you insist additivity of the entropy under independence condition, here has to be log something, and anyway the entropy always works well and somehow even magically works well. This is concave. Entropy is concave because T log T is concave. Concave in nu. And the entropy, we are interested in entropy growth. Entropy growth is that the entropy of mu T. HT is the entropy of mu T, and because we are working on finite graphs, it's always increases to the log g. This is a maximum. And HT, this HT is also concave function. It's stronger than concavity in nu. It's concave function in T if the graphs are transitive. So its graphs are like this, concave. And if the graphs are infinite, asymptotic entropy is this linear growth rate of HT. Because it's concave or it's subadditive, there's always limit. But in the case G is finite, this is of course 0 because HT is bounded above by log G and T tends to infinity, it's 0. And so the HD I showed you in the last previous slide is that it's asymptotic entropy of the simple random walk on the deregular tree. In this infinite graphs, infinite transitive graphs, there's a Shannon-Macmillan-Bryman theorem due to Deliak and Kaymanovich-Belchik that if you expect this log mu t xt, then it's log mu t xt expectation is log mu t x with the probability of xt is x. So it's like this, and it's ht, in fact, h mu t. So this is if you expect integrate it, you get h mu t, ht. And but this converges to ht pointwise. So the in this transitive graph random walk, somehow everybody sees the same scene. That it also says that this random walk is that's why random walk has something to do with fractal. But this theorem is of course vacuous when the graph is finite because everything tends to 0. This side, what? Yeah. And the theorem that which characterizes cutoff in terms of entropy is as follows. So this is easy, and somehow it's vaguely known to experts probably, but anyway. Expander family exhibit cutoff if for any delta and epsilon, so they can be same. One has at the time of mixing time of 1 minus epsilon means that somebody starts to feel that they live in a finite world, feel the boundary of the world. 1% of population start to feel the boundary. At that time, its entropy is already full, almost full. Log G is the largest maximum. If this happens, it shows it has a cutoff. My proof is uses the following fact. Simple that for given any new measure nu, in fact it's a mu t. If you move it by random walk once, p nu or nu p in the probability notation. By concavity, this p nu is entropy of p nu is always larger than entropy of nu, but it's at least constant times larger if the total variation distance is at least epsilon. So the at the t mix g 1 minus epsilon, if entropy is of almost log g, then there's not so much room for entropy to grow. But this says entropy has to grow at least constant until it's really mu t is really close to pi. So the mu t, once you get here, mu t becomes close to pi quite quickly. corollary to this, easy corollary to this is that this quantitative formula of Shannon-Macmillan-Bryman theorem implies cutoff. That if for any delta and epsilon, there is some time t. That's for after this time t naught. If you have this Shannon-Macmillan-Bryman theorem with uniform way, then the G has cutoff. I somehow believe this should hold always, but I'm not sure. I will explain this later, probably in the last slide. So now I give you a proof of Lubetzky-Peres theorem, one-page proof, except minute details. So by the previous theorem, that if cutoff holds if the entropy is almost full at the time of t mix 1 minus epsilon. And we know this time t mix 1 minus epsilon, the time when 1% of the population fills the boundary, is at least log g minus over hd. This is the entropic bound. So until this entropic time, if the entropy grows like this linear way, with growth is hd, then the entropy is, of course, it's almost log g, and you get the theorem. So this actually somehow always holds up to some finite time, up to injectivity radius. Up to injectivity radius, that's in the parent infinite group on the tree, it has Shannon-Macmillan-Bryman theorem holds, and it's always linear like this. And up to the injectivity radius time, they don't notice that they live in finite world or they live in the covering graph. So it grows like linearly, but at some point it breaks. But cutoff in this setting holds if it doesn't break at all until it hits the log g. Okay, then now I have to compute this ht minus 1, the increment of entropy at each step. Because entropy is given by this formula and its expectation log mu t xt. Increment is given by the expectation log of ft, function ft. Ft is a function given by this formula, mu t xt over mu t minus 1 xt minus 1. Mu t xt is population of your site, that xt is at some site, xt is at time t, this random walker is at some site, and you see how many population are there. That's a mu t xt. Mu t minus 1 xt minus 1 is t minus 1 step. So at the t minus 1 time t minus 1, at least 1 over d population moves at the same direction with you. So this value is at least 1 over d. And if you integrate this, it's almost 1, at most 1. So this function isn't that bad. It's not crazy function. It's tame function. It's always at least 1 over d. So the log is really nicely behave on this ft. Then you compute something. This is a punchline of the proof. For certain reasons, you compute this value. That's mu t is a probability, so it's L1. So I take square root and make it norm 1 vector in L2. Norm 1 vector in L2, and P applies this transition matrix P, adjacency matrix P, to square root of mu t minus 1 and hit by mu t and take inner product. This is P by x mu t minus 1 x square root. but square root is removed to moved to here. Mu t y. What? Yeah, y square root. And this is exactly the probability that xt minus 1 is x and xt is y. So that it's expectation of this, which is ft square root. So this side is this side lives in the probability side. It's in the omega and p, and this is just on L2G, and it's about functional analysis. Somehow my way of doing math is like judo. In judo, you grasp the opponent, and once you grasp the opponent, you pull it to your side, and then you can apply your technique. Yeah. So the anyway, this ft square root expectation is because it's here, it's dominated by this norm of this. Norm of this, if mu t is in the total variation distance, if it's far from pi uniform distribution, which means it's concentrated on a small area, it's almost perpendicular to pi, then it's of course perpendicular to, in L2 sense, it's almost perpendicular to the constant function. So that this is dominated by the spectral radius, reduced spectral radius of G, up to some error depending on epsilon. Of course, epsilon tends to 0, this tends to 0. If the people does not feel boundary yet. Now I want to compare this with a random walk on the covering tree. That's a deregular tree is covered by deregular graphs are covered by deregular tree, and random walk is covered by random walk, simple random walk on the covering tree. Then it's easy to check that and the ft tilde is the same. Ft tilde is the same ft, but it's xt tilde. Then it's conditional expectation of ft tilde with xt minus 1 xt, because ft depends on only on xt, and xt minus 1 is ft, almost ft. There's a slight difference in the boundary, but it's really negligible. Then because it's conditional expectation, concavity of square root and Jensen's theorem, that's what integration of square root dominates. Integration of square root is dominated by square root of integration. Yes, that's what this is. And the expectation of ft square root is dominated by rho g plus delta epsilon, but rho g does reduced spectral radius is almost reduced spectral radius of the deregular tree because of Ramanujan property, asymptotic Ramanujan property. So we get this estimate. Now, what is this ft tilde? Ft tilde is that everything is easily calculable for simple random walk on deregular tree. It's just you just calculate anything about the random walk on Z single line, but biased. You at the probability 1 over d, it moves towards the origin. At the probability 1 minus 1 over d, it moves in the opposite direction to the origin. That's what you look at, and easily you can calculate this. What is ft tilde? Except in the very negligible case, which the random walk is around origin. Ft tilde is almost d minus 1 when the random walk xt is closer to origin than xt minus 1 or tilde, and otherwise it's 1 over d minus 1. And so you can calculate the entropy increment in this case. Entropy increment is by probability 1 over d here, log d minus 1, but negative sign here. And the same probability d minus 1 over d, log d, here negative sign appears and cancels. So plus, so you get this value, which is exactly HD. So that's why asymptotic entropy of the random walk of the irregular trees HD agrees with the previous HD and agrees with Shannon-Macmillan-Bryman theorem. Next, I compute what is this EFT tilde square root. Now FT tilde square root is that the probability 1 over d, it's square root d minus 1, and the probability with this, it's square root 1 over square root d minus 1. And if you compute it, you get the exactly d square root d minus 1 over d, it's rho d. This is so the previous one, it should be true always, or it should be true anyway. But this rho d is something coincidence, or actually it's not coincidence, but because of the free group tree is so nice, it says that anyway this is some coincidence. That's a lucky thing that my proof hinges on. So it's rho d. That's it's almost the same as the expectation with ft 1/2. So this means that the expectation of ft 1/2 is almost same as the expectation with ft 1/2 tilde 1/2, and so the Jensen's equality in the Jensen's inequality holds almost. Jensen's inequality equality holds if and only if there's it's linear, it's a line, square root is a line, so that it's actually conditional expectation is not doesn't really do anything, which means so ft is almost close to ft tilde in this case. And so the expectation of log ft, the entropy increment of this random walk on the original graph is almost HD. That's it's same as tree random walk. And this finishes the proof. And all these approximation, nothing but happens because this f function ft is always at least 1 over d, and the integration is at most 1, then it's stable under perturbation. Last slide, I explain how one might solve Peres conjecture. So I review Kajmanovic-Vershik's proof of Shannon-Macmillan-Bryman theorem for transitive graph. So the Shannon-Macmillan-Bryman theorem, that's the log mu t xt, this is almost a constant. This is that's what Shannon-Macmillan-Bryman theorem says, or 1 over t, I mean. Log mu t xt is the sum of by telescope. It's like this. It's similar to the previous one. That's entropy increments here, but it's the direction is reversed. It's x0 to xt and x1 to xt, not the x0 to xt, x0 to xt minus 1. And anyway, I name it log g. I name it gt here. Gt is that so it's probability of x0 to xt and x1 to xt. And this is this has a different meaning. It's 1 over, actually 1 over d over conditional entropy. That's a there's the probability that a random walk hit this part at the time t, and the conditional entropy of that the random walk past x1 at the time 1. So anyway, this is also standard, at least 1 over d. And by telescope sum, it's there's a sk. Sk is a time shift of this cut some k parts. It's this doesn't make difference because graphs are transitive. Then by the martingale convergence theorem, this GT converges to some function, actually function on the Poisson boundary. Actually, this Radon-Nikodym derivative of some move of something, it has some meaning that G infinity. Integration of G infinity is entropy, Furstenberg entropy and entropy, asymptotic entropy. Anyway, because it converges and the limit function is a function defined on omega p, and omega p is a product space. So actually it's determined by almost determined by the first M letters because it's measurable with respect to this. Which means that you look at the xt, this value is something that the xt at the xt you ask neighboring population neighboring people that if you went through x1 or went through somewhere else at the first step, and this thing the answer the proportion doesn't change after m step or nearly doesn't change. This happens, for example, uniform if the G has, if the graphs, infinite graphs has uniform spectral gap, because this changes if there's another cycle coming in, new cycle coming in, starting from other to meet at somewhere. Anyway, this part uniform. And hence, central limit theorem says that so the G is almost determined by first M letter, and if K is larger than M, it's independent, becomes independent. This and this becomes independent if K is large. So the central limit summing T, huge T, and average it, you get central limit theorem says that it converges pointwise. The problem is, of course, that the infinite graph, xt starts to notice that the boundary, and things starts to change. And if this xt person notices it, and the other xt may or may not notice it, and it's not that simple. But still, if this uniform this convergence, martingale convergence thing holds, then you get the Shannon-Macmillan, quantitative Shannon-Macmillan-Bryman theorem, and you get the cutoff phenomena. Okay, that's all I want to tell you.
Okay, thank you very much.